Welcome to The Explainer. Today, we're taking a pretty incredible trip. We're zooming all the way from the massive macro scale of global power grids right down to the microscopic physics happening inside an electric motor. Now, it's literally the most common question out there right now about electric vehicles. Are EVs actually saving the planet? Or are we just, shifting the exhaust pipe from the car to a power plant 50 miles away? Well, let's take a completely impartial look at the data to find out. Here's our roadmap for this explainer. We'll start with the big energy picture. Look at the energy density challenge, peek under the EV hood, explore the magic of instant torque, and finally, wrap up with efficiency and maintenance. All right, part one, the big energy picture. To really figure out where energy gets lost and carbon gets emitted, we need to break things down into three crucial steps. First, there's well to tank, basically getting the energy to the vehicle. Then, tank to vehicle, which is converting that stored energy into actual mechanical power. And finally, vehicle to miles, which covers the actual physics of driving down the road. Because the truth is, the true ecological footprint of any vehicle starts way before you even turn the key. That well to tank upstream process, that accounts for all your power plants and energy grids. Then that tank-to-vehicle phase kicks in when the battery actually powers the car. You see, we can't just look at the car in a vacuum. We absolutely have to evaluate where its energy is coming from in the first place. And the numbers here are fascinating. An EV's carbon footprint depends almost entirely on its local power grid. If you charge an EV on a grid powered purely by coal, it emits about 29 kilograms of CO2 for every 100 kilometers. Believe it or not, that can actually be more than a traditional gas guzzler. But if you switch that same grid to natural gas, those emissions plummet to just 8 kilograms. And if the grid runs on solar or nuclear, those well-to-miles emissions effectively drop to zero. Moving on to part two, the energy density challenge. So here's the massive physical hurdle we have to talk about. Batteries have a huge, undeniable disadvantage compared to fossil fuels. Hydrocarbons, like gasoline and diesel, are just incredibly energy dense. They pack a massive punch. Lithium-ion batteries, on the other hand, are incredibly heavy and hold just a tiny fraction of that energy per kilogram. You basically need a mountain of heavy battery cells to equal the energy potential of just one single gallon of gas. Which naturally brings up a pretty interesting question. If batteries are that incredibly heavy and hold so much less energy, how on earth do EVs overcome this massive physical disadvantage to be so mind-bogglingly fast on the road? Well, let's dive into part three, under the EV hood. Let's quickly break down the architecture here. Think about the crazy complex plumbing of an internal combustion engine. Fuel pumps, lines, exhaust manifolds, a transmission with a dozen gears. Compared to that, an EV is remarkably clean and simple. You've basically got a charge port, a massive traction battery pack, a power converter, a thermal cooling system to keep it all from overheating, and the electric traction motor itself. That's the whole shebang. And that elegant simplicity is exactly how they recover the efficiency lost by carrying around those heavy batteries. Which leads us right into part four, the magic of instant torque. Torque is essentially turning force. And the amazing thing about electric motors is they can deliver their absolute maximum turning force the literal millisecond they start spinning, right from 0 RPM. This completely rewrites the roles of how a vehicle accelerates. Think about traditional gas engines for a second. They have to rev up to build speed, right? They're constantly hunting for that peak power band. But an electric motor, you hit the pedal and boom, maximum punch, instantly. It has what we call a flat torque curve, meaning the power is just there all the time, completely uninterrupted. When you look at how this translates to the real world, the stats are just wild. We're talking about rocketing massive, aerodynamically challenged 6,800 plus pound trucks like the Tesla Cybertruck or the Rivian R1S from 0 to 60 miles per hour in just 2.6 seconds. Guys, that is supercar territory, achieved by vehicles that weigh as much as a literal rhinoceros. And it's all thanks to that instant torque delivery. But hey, it's not just about raw brute speed. It's about brains, too. Advanced software controlling this torque makes the vehicle vastly more efficient. By making minute adjustments to the torque sent to the wheels, these smart systems can speed up acceleration by almost 28%, while actually saving up to 7% more energy. It's a total win-win. And that brings us to our final section, efficiency and maintenance savings. Engineers have come up with some incredible step-by-step technological innovations here. These systems can actually adjust torque dynamically based on how hot the motors are getting. They use clever tricks like coil switching, which is literally changing the motor's internal wiring on the fly, to optimize for either low-speed grunt or high-speed highway cruising. Plus, they use software sensors to monitor the motor's health in real time, allowing for predictive maintenance way before parts even start to fail.
And here's where your wallet will thank you. This mechanical simplicity and smart software lead to massive financial savings. Over the course of 30,000 miles, a gas-powered vehicle will cost you about 10.1 cents per mile in maintenance, adding up to over $3,000. An EV, just 6.1 cents per mile. That is nearly a 40% drop in maintenance costs. It's huge.
So where are those savings actually coming from? Well, right off the bat, no oil changes. There are just significantly fewer moving parts to wear out or break down. And perhaps the coolest trick of all, the electric motor can actually run in reverse to slow the car down, capturing all that kinetic energy and feeding it right back into the battery. We call this regenerative braking. It means your physical brake pads rarely even get used, which saves you from frequent and super expensive brake jobs. So let's wrap this explainer up. Despite the very real challenges of our current global power grids, and despite lugging around those massively heavy lithium-ion batteries, the electric motor itself is just an undeniable engineering marvel. Its pure simplicity is fundamentally rewriting the rules of performance, efficiency, and maintenance. Which leaves us with a pretty big question to ponder. As our global power grids continue to get greener, swapping out coal for solar, wind, and nuclear energy, will the massive mechanical advantages of the electric motor eventually make the traditional gas engine completely obsolete? Thank you so much for joining me on this explanator. Keep asking those big questions, and I'll catch you next time.